Our distinguished speaker today. So Bernd is going to tell us about algebraic varieties in quantum chemistry. And he actually asked to be the last speaker because he said probably everybody will be falling asleep and I will wake everyone up.
I don't know. Okay, anyway, thanks for staying. It's been a very, very nice day. The picture was taken in Berlin, this graffiti of the quadratic formula. And so there's a paper called Algebraic Varieties in Quantum Chemistry, and I wrote the co-authors over there. So Fabian Faulstich, so he's actually the person, he's our Stephen. So he's actually the person who connects us to quantum chemistry, and Swala is a PhD student in Berkeley, and I'll tell you more about her later. We will have a research program in IPE NSF permitting. We will have a research program at IPAM in Los Angeles in the spring of 2027. So Frank and I are among the co-organizers, and it's four quantum chemists and us. So if you have any questions about this topic or maybe how to participate, you can also speak to Frank. So let's start with linear algebra. I'm going to fix two integers, n greater equal d, positive, and I'm going to look at strings I1 up to ID of increasing sequences. So they index the standard basis for the exterior power, the dth exterior power. So E sub I, I'm going to write for the standard basis vectors. And the vectors in this space I'm going to call quantum states. So psi is a long column vector, and with coordinates psi I, and so n choose d, that's the d element subsets among the first n positive integer. So let's say a scientist gives us a symmetric matrix H with this many rows and columns, and this matrix is called the Hamiltonian, and we're asked to solve the eigenvalue problem. That is to say, we'd like to find a scalars lambda and column vectors psi, such that this equation holds. So maybe all of them, maybe one of them. Now this sounds like an easy problem, right? You've all seen this in undergraduate or even before, but it turns out it's not very easy at all because n choose d is very large. So in this scientific application, n choose d is large, and this is the whole difficulty. What should you do if n choose d is large? Now, one approach that's very popular in quantum chemistry is called coupled cluster theory. And from my understanding is that this takes this problem, which is a large, very large problem of linear algebra, and replaces it by a smaller problem, a small problem of nonlinear algebra, right? So we're shifting the complexity from the size of the matrix to nonlinearity. Now, this is, of course, nice, right? Because I like nonlinear algebra. So a shameless plug, we have this book with Mateusz, organizer this week, called Invitation to Nonlinear Algebra. So, of course, I like nonlinear algebra. But whether this is a good idea or not, I am agnostic. So I'm not passing judgment whether this is a good or whether coupled cluster theory is a good or a bad approximation. That's up for the chemists to decide. What I can do as an algebraist, I can provide tools, I can provide insight for them that helps them in making that judgment. Okay, and that's what we're going to do. Again, so there's the paper with Fabian and Swala. So what we do is we develop some relevant algebraic geometry for CC theory for quantum many-body systems. We're going to get to the electronic Schrödinger equation, which is related to but different from the Schrödinger operator we saw this morning. We're going to talk about the exponential parametrization, and the Grassmannian will also make a big appearance in this talk. So the 2x4 matrices satisfy the Plücker relation. We'll see that. So I will also later show how to derive the Hamiltonians, and in the end talk about the CC equations, coupled cluster equations, and the degree.
So do the chemists really care about R and N and symmetric matrices, or do they care about Hermitian matrices?
They actually care about real symmetric matrices. There's also complex versions, but in this particular problem, they actually care about real symmetry. Yeah. Okay, now let's duplicate our vector space. Let's do two copies. So the first vector space, so this is again, the n choose d-dimensional vector space. I'm going to call this H, and those vectors I'm going to call the quantum states. And then there's a second copy called V, it's the same vector space, and those vectors I'm going to call cluster amplitudes, right? So there's two versions of the same vector space, the quantum states and the cluster amplitude. I'm going to write E sub bracket D. So bracket D is the string 1, 2 up to D. So this is the first standard basis vector or the reference state. The reference state is the first standard basis vector. So they're using something called the exponential parametrization, which is a bijection, a nonlinear bijection between these two vector spaces. So it takes an X, a cluster amplitude, and makes a quantum state. And here's what you do. There's going to be a certain square matrix, T of X. Then you apply the exponential to this matrix. That's going to be a new square matrix. And then you just look at the first column vector, right? So multiplying this square matrix with the first basis vector extracts the first column. So this is a certain map. So to define this, all I need to tell you is what is T of X. Now, first of all, T of X is a strictly lower triangular matrix. So it's an n choose D by n choose D matrix. Every non-zero entry is one of the up to sign, one of the coordinates of the cluster amplitude. So every entry is a cluster amplitude, plus or minus. Now, of course, being strictly lower triangular, the matrix is nilpotent, but in fact, it's very nilpotent. It turns out the D plus first power is already the zero matrix. Right? So T is a nilpotent matrix. Now, therefore, the exponential is a unipotent matrix. And because of this property here, the entries of this exponential actually truncate, right? So these are polynomials in the x's of degree at most D. Okay, so these are the properties that this matrix has. So therefore, this will be a polynomial map. This will be a polynomial map, and it will be a bijection. Okay. Let's do an example. So if D is 2 and N is 5, so then N choose D is 10. So in this example, the matrix T looks like this. So it's a lower triangular matrix, and every entry is x12, x13 up to sign, up to x45. Now the exponential of this matrix has ones on the diagonal, and then the entries are down here, and then you have a little bit of nonlinearity down here. You see x14 times x23 minus x13 times x24 plus x43 times x12, which happens to be 1 on this affine chart. Okay, so that's a first example. So there's a very interesting block structure. Everything is interesting about these matrices. Okay, this is all very interesting. Okay, maybe, maybe not. Let me first tell you, sort of in down-to-earth terms, what this matrix is. So the entry in a given row J and column I, so I and J are D subsets out of 1 up to N. It's 0 unless I minus J is in the first D. So everything that's in I but not in J is in the first D, and the other ones are in the last N minus D. Right? So J minus I has to be in the last N minus D. Now, if this holds, then there is a non-zero entry, and the entry up to sign is the sort of symmetric difference, right? So you take the first with D union I minus I, so it turns out that that's a D element set, and there's a combinatorially defined sign. Right? So this is the combinatorial definition. Now, the rows and columns are ordered in a particular way by increasing level, and I'm going to define the level of a coordinate. It's either a coordinate of psi or a coordinate of this amplitude, and it's simply the cardinality of I minus D. Okay, so let's go over what I mean by level. So if D is 3 and N is 6, so again I have these two long column vectors. So psi is a column vector of length 20, or element in the exterior algebra, exterior power, or this vector x, 20 coordinates. So there's one coordinate of level 0. There are 9 coordinates of level 1, 9 coordinates of level 2, and then there's 1 coordinate of level 3. So level is just the number of indices outside the first d guys. Okay, and I'm just respecting this level the way I organize the, okay, so here you can see, first row, so that's level 0, then there are 6 rows of level 1, and then there's level 2. Okay, let's work it out. So again, here's the exponential parametrization. So I take my matrix, then I have this unipotent matrix here, and I extract the first column. So for example, if d is 3 and n equals 6, these are the 20 coordinates of my map, right? So, and in a given level, in the ith level, I have polynomials of degree I, right? So the most complicated one here, we have these sort of Plücker-looking quadratic expressions, and then down here for the level 3 coordinates of psi 4, 5, 6 is this expression. So this is a map from, well, 19-dimensional affine space, or maybe P19 to itself. So later on, I'm going to homogenize this one and I'm going to work projectively. So this is a map from 20 space to 20 space, and we'll see in a moment that this is invertible. In fact, so proposition, this map from V to H has a polynomial inverse the other way around, and the inverse almost looks like the forward map. Namely, if I take my system, it has this triangular form, I can invert it. So I claim that each xi is up to sign psi I plus a polynomial in psi coordinates of strictly lower level. Right? So let's just go through this, right? So here, the psi's are written in terms of the x's. Well, I can just put the x's on the left side and the psi's on the right side. Then here for these quadratic ones, right, I can put the x on the left side and then the psi on the right side, but then these x's have lower level, so therefore they're already written in psi's and so on, right? So this is already triangularized by level, and it's very easy to see that there's a polynomial inverse, and here's the formulas, right? So you can now write the x's in terms of psi's. You might have some factors here like a 2, but basically there is an inverse. So I know what you're thinking, JM. You're thinking, where's the representation theory? And that's what we were thinking too when we wrote, and we didn't know. We couldn't figure it out, right? So we were now there's more coming. This is from the first paper. We did a lot of things, but I felt a little bit unsatisfied by this paper because I didn't, understand the structure. Of course, advisors love to brag about their students. So this morning, Swala has a single authored paper on the archive. It's called the truncation varieties in second quantization. That takes this much further. And I think she also gives a very good explanation, sort of representation theoretic explanation. There's something called the Fermat-Dirac algebra, which is a particular Clifford algebra. And so I invite you to take a look also at that paper, okay? But let's go on in the more pedestrian way. Let's do a little bit of combinatorics. So Alberto already showed how nice combinatorics can be. So let's actually look at these formulas. So all the coordinates of the experimental parametrization, they all look alike, right? They all come from labeling, relabeling a particular master polynomial. Namely, what I'm going to do is I'm going to take n to be 2d. So then I have the d early indices and d late indices. And then all the expressions look like this. So the x can be written in terms of psi like this. Then the level 3, I have this cubic, affine cubic. Level 4, I have this quartic. And finally, I have this quintic. And so in my parametrization up to relabeling indices, every entry looks like this, right? So they all look alike. You can see this, right? So the level 1s are all like this, the level 2 are like this, and then further down, so there's sort of these master polynomials. So Well, look at the number of terms in this master polynomial, you count them, right? So the quadratic has 3, the cubic has 16, 131, and so on. So you go to the online encyclopedia of integer sequences, and this is a nice number, right? So it turns out the similar, for the inverse, the number of terms is the same. And there's explicit formulas for the master polynomials and the forward and the backward direction as explicit integer linear combinations of monomials. And these monomials represent what's called uniform block permutations on an even-sized set. This is kind of interesting. This is actually an active area of research in algebraic combinatorics. So there's Rosa Orellana and her collaborators. So they have papers. So these things have a Hopf algebra structure. So there's some, Frank likes Hopf algebra. So there's some very nice algebraic combinatorics and simply writing down each coordinate of the exponential parametrization. And it gets even nicer in the new paper.
Like the antipode, the inversion?
Yes. And you can exactly say what all the, I mean, you can see here 24, 6, you can say exactly up to sign what these are, what the coefficients are, okay? Very good, so there's some nice combinatorics. So we'd like to talk about the varieties, and these are so-called truncation varieties. As I said, today's paper is called truncation varieties and second quantization, but my talk here is about first quantization. So let's fix a subset sigma of bracket D. So I'm fixing a subset sigma of the non-empty subset of the first D positive integers. What I can do, I can restrict my bijection to the coordinate subspace whose coordinates have prescribed level. Right? So for example, let's say D is 4. And Seth and I, we like 1 and 3, right? So sigma is 1 and 3. Then we say, let's look at all those coordinates that have level 1 or level 3, and we're simply restricting our bijection to that linear coordinate subspace. Well, we could do that, right? And the image of this restriction is called the truncation variety. So it's truncation variety, truncation at level sigma. Okay. So by definition, V sigma now is a variety in the projectivization of the V space, the cluster amplitude space, which is a projective space of this dimension. It's a sort of the Plücker space. Now, of course, this truncation variety, anyway, the affine part is very easy, right? I have a bijection, I have a polynomial map that's forward, and I have a polynomial map that's inverse. So I know this variety. It's smooth, and I know the dimension. And the dimension of this variety is the number of coordinates that have allowed level. Right? Well, that was very easy. But I'm going to take the complex projective closure. I'm going to study this variety now as a projective variety. So I defined it by this affine polynomials, but I now look at it in this projective space. Let's do some examples, just to kind of get a feeling how this goes. So let's say D is 3 and N is 6. So a 3-element set has 6 non-trivial subsets, like 6 non-empty proper subsets. So there's 6 truncation varieties, and 3 of them are sort of trivial. They are linear. So if the truncation sigma is the singleton 2, or the singleton 3, or the singleton 2, 3, then these are uninteresting. They're going to be linear varieties. So for example, the first one is just a flat P9 or P1 or P10 inside the ambient 19-dimensional projective space. So those are the uninteresting ones. So the interesting ones are the nonlinear ones. So if sigma is, for example, 1 and 2, well, then that's a hypersurface, right? So then by this formula, there's only, one coordinates that's not allowed, right? There's only one, level 3 coordinate, and therefore it's just the hypersurface defined by the homogenized master polynomial. So x456 was this master polynomial with 16 terms, and then we just homogenize it. So there's a cubic polynomial with 16 terms. That's this hypersurface. Well, then the 1,3 truncation has dimension 10. degree 41, its prime ideal is generated by 25 quadrics. And then if sigma is the singleton one, then we get the Grassmannian. Right? Then we get the Grassmannian G36, which is 9-dimensional, has degree 42, and the ideal is generated by 35 Plücker quadrics. Right? So we see a familiar friend here. We see the Grassmannian. We see 3 linear spaces, and we see sort of 2 new varieties, right, in this example. Okay, Coxeter-O'Shea. So what's the first thing to do? So according to the last chapter of Coxeter-O'Shea, we can compute the homogeneous prime ideal by a saturation, right? So, well, on the affine chart, I had this polynomial bijection, so that was very easy. So if I restrict my variety to the affine chart where the first coordinate is 1, then by definition, my variety is a complete intersection. I simply took all the coordinates I want to kill, I make them 0. So that's a complete intersection. Whoops, sorry. Here we go. But then if I saturate at that variable, then I get the homogeneous prime ideal, right? So I take all the affine equations, so I take all the polynomials that have a disallowed level, I homogenize them, and then by the last chapter of Coxeter-O'Shea, to compute the homogeneous closure, I have to homogenize the polynomial and then saturate the homogenizing variables. Right? So that's going to be the ideal of the truncation variety. Now we saw in my example that 3 of them were linear and 3 of them were nonlinear. So let me give you a little theorem that characterizes when you get a linear space. Okay, so I claim the truncation variety V sigma is a linear subspace if and only if a simple condition holds, namely the index set sigma is additively closed. And by additively closed, I mean that if I and j are in the allowed levels, and if I plus j is not beyond d, is still within d, then also I plus j should be allowed, right? So the allowable i's should be additively closed in this sense. And now you go back here, right? So you can see these are additively closed. So therefore they're linear spaces. And these 3 are not additively closed, right? So the set 1, 2 is not additively closed in bracket 3 because 1 and 2 are in the set, but 1 plus 2 is not in the set. But here, if you take these, for example, 2, 3 is additively closed because 2 and 3 are in, but 2 plus 5 is beyond. Right? So therefore, this explains when we are linear.
1, 3, isn't 1, 3 also closed?
1 plus 1 is 2.
1 plus 1 is 2.
1 plus 1, you
Yeah?
can also
Yeah. You can also. So 1, 3 is not closed, right? Because 1 is in, but 1 plus 1 is not in. Is this clear? So it's a very simple, yeah. So add in a very naive sense. So additively closed means the truncation variety is linear, and that's going to be the uninteresting case. We're going to be interested in the nonlinear varieties. Okay. Okay, so that's sort of a couple of basics about these things. I should repeat the question, right? So question for people in the other room is, why is the set 1, 3, not additively closed? That's because 1 is in the set, but 1 plus 1 is not. Okay, so the observation about the Grassmannian, that's a theorem in general. So in general, for any d and n, if sigma is the singleton one, so if sigma is just the singleton one, then indeed the truncation variety recovers precisely the Grassmannian in its Plücker embedding. Right? Now, if you know and like the Grassmannian, then this is sort of good news, right? That means the V sigma are generalizations of Grassmannian. So these are some other varieties that in a very, very natural way generalize the Grassmannian. Now, the Grassmannian has a duality, and that holds actually for all truncation varieties. So the next proposition, so if sigma, we're again fixing a set sigma of allowed levels. Let's assume n is bigger than 2d. then I claim there's always a linear isomorphism, there's a linear endomorphism of this ambient projective space, which switches the two truncation varieties. Right? So the Grassmannian, we know this, but this will be true. So the dn truncation variety for my choice of sigma maps onto bijectively onto the n minus dn truncation variety. Okay, let's do another table, this time with numbers. Okay, so now let's take d to be 3, n equals 7. So d is still 3, so there's still 6 non-trivial subsets. And let's organize them in the columns, right? So I have the singletons and the pairs here. And for each of these varieties, I'm writing the dimension. So 12, 18, 22, now n is 7, right? And then I'm recording the degrees. Now you have these entries 1, that's the case when they're linear. So those are the linear varieties, the additively closed linear varieties that are not interesting. And then here, the Grassmannian in this case has a degree 462, and it has 140 quadratic Blocher relations. So min gens, so this says, for example, this variety, the 1,2 variety is defined by 7 cubics. The 1,3 variety is 76 quadrics and 10 cubics and so on, right? So in general, there are quadrics and cubics for the nonlinear variety, so they're not just highest rate orbits, there's some other varieties, okay? And now besides the degree, there's one more number here in orange, that's the so-called CC degree. It's the coupled cluster degree, and we're going to get to that. That's actually the number of solutions, that's some other system of polynomial equations, that's the one we want to actually compute. So I'll define later what this coupled cluster degree is, but whatever it is, it's a little bit bigger than the degree of the variety. Okay, same table, just to kind of do some more, right? So if D is 4 and N is 8, now the ambient Blocher space is a projective space of dimension 69, just one less than 8 choose 4. Now a 4-element set has 14 non-trivial subsets. And 5 of them are linear, right? So these are the additively closed ones. These are uninteresting. And the 9 interesting ones are the columns of this table. So the notation is the same, right? So here are my chosen truncation set sigma. And these are the various dimensions. So you can see this grows already quite a bit, right? So for example, this last one is a 33-dimensional projective variety in a 69-dimensional space. This variety has degree 12,012, and the ideal is minimally generated by 236 quadrics and 200 cubics. That's this notation. Yeah, you can see, I mean, even here, this is sort of interesting, right? For example, this one is 52-dimensional, but there are 16 linear equations. Actually, there are 16 linear equations and 1 quadratic equation. So therefore, the degree is 2, right? So these degrees vary quite a bit. And then in orange again, you have the coupled cluster degree, which I have not yet defined.
So one of the non-Grassmannians is the same degree as the Grassmannian, and the other one is half that.
Isn't that interesting?
It's super.
That's super
Because
interesting.
you know, that's a highly divisible number because it's in the young capital. So
It's
interesting combination.
Victoria is smiling. She really likes these problems and she likes to solve them. Okay, so yes, it's interesting. Okay, very good. So we reached a half of the talk, slide 13 out of 15, and there's a reception. So we'll try to be in time for the reception. Okay. So now let's get to the coupled cluster degree and to the coupled cluster equation. So remember what we wanted to do originally. The original problem was to solve a big linear algebra problem, an eigenvalue problem. We want to now replace this by a nonlinear algebra problem. Here's what we do. We take our eigenvalue problem, which is h psi equals lambda psi, but we're only looking at the coordinates with allowed level. So Seth and I, we agree on what level is allowed, and we throw in this vector equation, h psi equals lambda psi, that's a long column vector equals to some other long column vector. We only keep those equations whose index is allowed level. Now then, of course, that's under constraint. That's a highly under constraint problem. But to make up for this, we're requiring our eigenvector to be in the truncation variety. Right? So what I'm saying is, I'm looking at my eigenvalue problem, but I'm looking only at eigenvectors, so eigenpoints projectively, only eigenvectors that lie in one of these varieties. Now that would be over constraint, but I retain just the right number of linear equations. So it turns out that this is a well-constrained problem. It has finitely many solutions, and that number of solutions is the CC degree. So it's the coupled cluster degree that depends on D and N, and of course on sigma. This clear again? You have this eigenvalue problem for a very, very, very long vector, right? You throw out many of these coordinates. You only say this coordinate. Now you've thrown out too many, but you make up for this by requiring that psi is in some variety. Okay. Very good. So this is the CC degree, and we saw some numbers, right? And we'll talk more about this. Yes, John, you have a question. Yeah, so the question is, what does choosing sigma mean? What are these different models? So yes, think of them as different models. And I'll explain this to you now in terms of electrons and so on as the talk goes on. Yes. Yes. Can you say this again, please? Single and double excitations. Very good. This gentleman in the last row knows what he's talking about. Okay. Very good. Now, I didn't know anything, right? But luckily, we have somebody on the team who knows something, right? So I said, okay, now we started computing. We have some Grassmannians and nice varieties. But what's H, right? I need to understand and maybe convey to my audience what's H and where does H come from? And now I'm going to embarrass myself. So you have to like help me out, okay? So I asked, where on earth does this H come from? Well, so this comes from the electronic Schrödinger equation, okay? So here's what's going on, right? We have a differential equation. So psi is an unknown function in 3D variables. So we have a system with d electrons, and each electron has a position in free space, right? So, and Ri is the position in free space, real free space of the ith electron. So then, this density function psi is a function of these d vectors. So there are 3D unknowns. Now this satisfies a number of things. So this function is skew symmetric. That's called Pauli's exclusion principle. So skew symmetric means that if I swap an Ri and an Rj, then I pick up a minus, right? So there's some skew symmetric function of these d vectors. Now what this says is this is an eigenvalue, it's an eigenfunction of this operator H. So this operator H, the Hamiltonian, looks like this. It looks scary, but it's not so bad at all. So it's the sum of d Laplacians. So delta Ri is the Laplacian for the ith vector. So and this just has 3 coordinates, right? So Laplacian is the second derivative with respect to x, plus the second derivative with respect to y, plus the second derivative with respect to z. And you do this on each of the electrons, there's a minus a half, and the rest of it is just multiplication, right? The differentiation is here, and this just says we're multiplying by minus this stuff and by plus this stuff. So what is this stuff? Well, we have more parameters here. So R sub j are the location of fixed nuclei. Right? So they're electrons and nuclei. These are atoms, right? And this is a potential. These are all potentials, right? So there's a integer zj. So I runs over all electrons, I from 1 up to d. J runs over all nuclei, 1 up. So d nuke is the number of nuclei. And then, so here the potential is the distance between the ith electron and the jth nucleus, right? That blows up. And then here's a corresponding expression for the pairs of electrons, okay? Now then, what's the zj? The zj is a positive integer, and that's the number in the periodic table. Okay, the periodic table, these elements, they're labeled 1, 2, 3, that's the CJ. That's the number in the periodic table. Now, the number of electrons should be at least the number of nuclei, right? So every nucleus has some electrons that sort of go around it. So there's an inequality, and then D, the total number of electrons, is the sum of those ZJ. So if you're an atom in the periodic table and your number is Z, then you have Z electrons. Okay, so I said, that's great, Fabian. Can we actually make a matrix, right? And he said, okay, we discussed. Okay, so here was a small example, but this was really quite fun. So we worked this out for lithium hydride. So lithium hydride is LiH, okay? So Li is the second one, right? So third one, sorry, this is the third one. Yes, yes, so 1 plus 3. So this has 2 atoms, 1 lithium atom and 1 hydrogen atom. So the total number of electrons is 3, thanks Frank, for the lithium, and 1 for the hydrogen makes 4. That's our D. So D is 4. So there are now two loose nuclei. So they're at locations capital R1 and R2. But then we're interested in these 4 electrons, and they are at variable locations. So our wave function is an unknown function of 12 scalars. Okay, great. So now we're going to make a matrix out of this. I want to do this algebraic geometry now. So how are we going to do this in matrix? Well, we need to discretize, right? So Frank, yeah.
What is location?
The point in space. Just so I'm here, right? My coordinates are 3, 7, 11. Location is just a point in space, okay? So the way we're going to discretize is the following, right? We're saying let's restrict the Hamiltonian to a subspace of nice functions, okay? And these are called atomic orbitals. So there's some catalog of functions that the chemists like, and they're on a website, right? So there's a website, and there's functions chi1, chi1 up to chi-k, and that's the repertoire of functions we're going to choose from, right? Now, of course, there's 100 years of chemistry, right? I mean, there's all of spherical harmonics. There's many, 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 many thousands of papers that have been written, and they have agreed that these are the functions we should use, and they're on a website. So we're going to restrict to this subspace. So, and K has to be at least 2. So we decided, let's do this for lithium hydride. So D was 4, and let's restrict to K equals 4. Okay, so we're selecting out of this database 4 atomic orbitals. And these are, functions on R3 that are rotation invariant. And these are graphs of this function. Okay, and so blue says the value is positive, red says the value is negative, and don't ask me to explain this. These are the pictures you saw. Even back in high school, you didn't understand that. Okay, okay? And we don't. Anyway, so those are these functions. They're called orbitals. Okay. Now there's one more twist. Yes.
Sorry, Ben, are these functions now the basis of your three-dimensional?
Yes. So I picked 4 functions, and each of these pictures represents one of these functions. Each of these is a function from R3 to R, and it's the function that they like, and it's on a database. Okay. So now there's one more twist. There's something called electronic spin. Okay, so electronic spin says we should double the number of functions. So we should go from K equals 4 to n equals 8. So n is twice K. So the natural choice for lithium hydride is D equals 4 and n equals 8. And that is the Grassmannian we like. Okay, and there are 4 more. Now we have 8 pictures. And these are 8 functions. They come in 4 pairs, and the pairing has to do with spin. And they're snickering in the back. Okay, so later on after the talk, during the reception, you can talk to these guys back there who know what's actually going on. So now we have to compute the matrix H from the operator H, right? So we have this H is a differential operator, the Schrödinger operator. We're now discretizing, and this is a 70 by 70 real symmetric matrix. So we're going to do this now. So now we have a basis of molecular orbitals. So this is psi1 up to psi8. Now to fill these matrices, we need an inner product on this space, and that's an integral over R3. Right? So the inner product of 2 of these functions is the integral. You multiply these values, and you take the rotationally invariant integral over R3. Okay? Now you have these functions on R3. Now you lift them to an exterior power, and they call this a Galerkin basis. So going from these 8 functions, we now go to 70 skew-symmetric d-partite functions. So what we do is we just wedge these functions together, and we're calling them capital psi, and I is one of our subsets, right? So now we're going to lift the inner product to the exterior power. So now we have these 2 of these Galerkin functions, and we lift the inner product, so we're summing over all elements in the symmetric group, permutations of the indices I, permutations of j, and then we multiply the corresponding integral values, right? So to evaluate all of these things, you need to integrate functions over R3 in Julia, okay? Okay, now we're done, right? So now we have the entries, right? So I have the 70 by 70 matrix, and in row I, and in column J, I put a floating point number, and it's this number. It's the inner product of this Galerkin function times the Schrödinger operator applied to that Galerkin function. Okay? I'm now done. Now I have a 70-70 symmetric matrix, real symmetric matrix filled with floating point entries. Okay, there we go. And we described this in the paper. Now, of course, this was very boring, right, for the people, but I felt that that's very useful, you know, to go through this computation once for the algebraists to see where these matrices come from. Because later on, when we go to IPAN, when we have this special semester, it's going to be the structure of the Hamiltonian that makes all the difference, right? We want to really understand not just the structure of the variety, we also need to understand the structure of the Hamiltonian. But here, this is just some way of making a 70 by 70 symmetric matrix.
Yeah, it's remarkable. This is like the smallest molecule. Page 2.
This is the smallest molecule. Okay, so Fabian and Swala, they have a project right now. It's very fun and very hard. They're trying to do water. Okay, they are. So stay tuned. Okay, they're working on water. Okay, so let's go back to the math. Right? So let's go back to numerical algebraic geometry. So here are, yes.
Sorry, this is a stupid question.
There are no stupid, they're only stupid.
Why is it the structure of the Hamiltonian?
Well, so the question was why, why does the structure of the Hamiltonian matter? Well, we want to now solve a system of polynomial equations, right? So now in the system of polynomial equations, well, there are real solutions, there are complex solutions. We'd like them to be real, right? They should ideally model the eigenvectors of a symmetric matrix. And we'd like to have the number of solutions to be small, right? So I will tell you now for random generic symmetric matrices, there's this orange coupled cluster degree, and it's what? 24,000 something, right? Exactly. But of course, let's say 24,000, a big number. It would be much nicer if the number were 8, right? Like 8, you liked 8, right? So that would be nicer, right? But to get there, maybe we can exploit special structure on H, but we will not do that in this talk. In particular, this talk has only 16 more minutes.
So the coupled cluster degree, this is for generic symmetric matrix.
That is for a generic symmetric matrix. So for generic symmetric matrix and an n and a d and the sigma, there's a number, and it's the number of solutions to this system of polynomial equations. Okay, let's discuss that number. Right? So for example, if d is 2 and n is 5, sigma is 1, so this is the Grassmannian, G25. So the Grassmannian G25 has coupled cluster degree 27. So let me explain this to you. So first of all, here's the equation of the Grassmannian, right? It's the rank of this skew-symmetric matrix is of rank 2. So this is equivalent to the 5 quadratic Plücker relations. But then I also have the eigenvalue equations, right? So I take this column vector of length 7. I take the corresponding here column vector of length 7, right? So I deleted the 3 non-allowed coordinates, right, that are not allowed. So now I have this variety, the 2 by 2 minors here, and the 4 by 4 Pfaffians there. And I claim that this together has 27 solutions in P9, and H is a random 10 by 10 symmetric matrix. Okay. Now the number 27 happens to be 2 times 14 minus 1. So I'm going to give you a formula now for the 2n Grassmann. But before I do that, let me give you a general degree bound. So a general degree bound says the number of isolated solutions, so the coupled cluster degree, is bounded above by Bézout's theorem. So by Bézout's theorem, I have the degree of the coupled cluster variety, whatever it is, times the degree of the Segre variety. Right? So here, this one gives me the degree of the Grassmannian. This one is the 2 by 2 minors of a fairly general matrix. So this is simply a variety of minimal degree. This is just the degree of the, this is just the dimension plus 1. Right? So for example, in the 2,5 Grassmannian, the upper bound is 35. So it's 7 times 5, and 5 is a Catalan number, and that's a little bit bigger than 27. Now, one corollary to this is the only time when this inequality is tight is in the uninteresting linear case. So in the linear case, when this degree is 1, then of course we have equality and all complex solutions are real, but that's additively closed set. That's a case that's not interesting. Okay. Okay, so the 2n Grassmannian is all about the Catalan numbers. So the degree of the 2n Grassmannian, as many of you know, is the n minus second Catalan number. So the Catalan numbers are 2, 5, 14, 42. And in the original paper with Fabian and Swala, we conjectured that the coupled cluster degree is this binomial coefficient. We didn't realize back then immediately that this was 2 times the earlier Catalan number minus 1, but the next one minus 1, but Victoria came along, we worked this out, and there was a subsequent paper with Victoria Borovic, and we're proving this, right? So the coupled cluster degree of the 2n Grassmannian is this number, and here you now can look at so this is the actual CC degree, there's the bound for n equals 4, 5, 6, 7, and so on, right? So it's a little bit smaller, right? So this was a conjecture in the original paper, and then literally 2 months later, there was an idea. And the proof is actually quite nice. So this involves, toric degeneration. So some people call this Newton-O'Kunkov bodies. We call it Hovansky bases, especially in Toronto. Anyway, so there's a nice story for the 2n Grassmannian. And we do not know, I think, the coupled cluster degree for the general Grassmannian. It's an open problem, right? So we worked this out for the 2n Grassmannian, what we don't know in general. Now, in the new paper that came out by Swala this morning in second quantization, it's much more general. Other classical varieties occur. So the spinor variety occurs very, very nicely. And also certain 3-step flag varieties occur very, very nicely. So I encourage you, to take a look at the old paper and the new paper. So it's really quite interesting. So among these varieties, there are some that are sort of classical that we recognize and love, and they're quadratically defined. And then there are some others, right, that require higher degree generators. This is about the hypersurface case. So if n is 2 times d, and our choice of sigma is everything except d, then the truncation variety is a hypersurface. There we also have a result. So there the coupled cluster degree is the upper bound minus d minus 1. It's this expression. And just one time, at the very beginning, we had the 6 truncation varieties in P19. That's for d equals 3 and n equals 6. So, and these are the nonlinear cases. And in each case, there's the bound, and there's the coupled cluster degree. So the 1, 2 case here. So it's a cubic hypersurface of coupled cluster degree 55, and the upper bound is 57. And I'm going to come back to this number 55 in a moment. Okay, so 55 is the coupled cluster degree for d equals 3, n equals 6, and sigma is 1, 2. Now, of course, we didn't start this, right? There's an enormous literature on the subject. And so here is a slide on previous literature. So one aspect of the previous literature is Fabian's paper with Matthias Oster that appeared last year in Siaga, called Coupled Cluster Theory Towards an Algebraic Geometry Formulation. Right? So this was Fabian's idea. There was a huge literature on the chemistry side, and he had this idea. He really would like to talk to people who know about polynomial equations. So he contacted me in maybe 2020. He sent me email. He wrote an email. I didn't understand anything. The guy kept persisting, go away. I'm not even in Berkeley, And so this went on for a little while, but he kept sending me emails, and then eventually I went to Berkeley, and literally, 9 months later, I understood something, right? So this is very typical, right? I mean, you talk to somebody and you don't understand anything they're saying, right? And in particular, the first version of this paper, I didn't understand what they were talking about. In any case, it eventually made it into this journal, which is a pretty good journal. And section 6 of this paper talks about the CCSD model for 3 electrons in 6 spin orbitals. Okay. Now, in our notation of this lecture, that means that D is 3, N is 6, and sigma is 1, 2. CCSD means coupled, cluster, singles, and doubles. So SD means sigma is 1, 2. Now, then they go on, and I'm citing from the paper, that this case supersedes the ability of state-of-the-art algebraic geometry software. And in theorem 4.10, they use Bézout's theorem, which applied people actually like. They use Bézout's theorem to derive an upper bound for this coupled cluster degree, and they write the upper bound, that's 2 to the 27. So that's about 134 million. But you know that the answer is 55. Right? We just derived it. Right? So this is a conceptual progress. This is not a progress, and computers are better. It's just we analyze the structure, right? So if you just naively, so they did a very important step in this first paper, and the very important step was actually making the connection to algebraic geometry, right? Yeah. And now in the paper I'm talking about now is we took this and we looked carefully at the algebraic and combinatorial structure, and we made further progress. And actually, in some cases, getting now, of course, if you have a polynomial system with 55, that's a minimal problem. That's like you can do what in a millisecond on a chip or something. That you can do fast. Right? This you can't do fast. Right? Now, of course, comes the next step. There were many things in this paper that we didn't yet understand, like what's actually the representation theory. And again, there's Fermi and Dirac, names of 2 physicists we heard about already in the morning. Now, here's a theorem that relates our new result to the classical literature. And it turns out that our result is not quite the same. So let me state it like this. So our formulation in this paper of the CC equation is equivalent to the classical equation. So let me call this the classical equations, if and only if sigma satisfies another condition. And the condition is that sigma is an arithmetic progression inside its interval. So an arithmetic progression says that sigma looks like this: m, 2 times m, blah, 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 up to k times m, for some integers, m and k, up to d. No, I don't have to reach. So for example, m by itself. So the singleton one, the Grassmannian case would be an arithmetic progression, but it's not a. Now, why is this good? Well, this covers all the models that were ever, as far as we know, that were actually studied in the computational chemistry literature. So for example, CCS, singleton 1, Grassmannian, CCD, singleton 2, CCSD, 1 and 2, singles, doubles, triples. So those are the ones that actually occurred in the literature. They are all arithmetic progressions. Of course, 1, 3 would not be an arithmetic progression, right? So there are some models, some truncation levels that there's a deviation. Their equations are a little bit different. But all the models that appear in the literature are covered by our new formulation And again, the literature is vast, right? So here's one example, from 2000, so complete set of solutions of multi-reference coupled cluster, blah, blah, blah. Now, back then, 25 years ago, people knew about homotopy methods, but when they used homotopy method, they used them to find one solution. Right? So they used homotopy methods was used many 50 years ago, right, to find one solution. What we can do now is to find all solutions. Let me slowly wrap up. So we solved a couple of cluster equations, homotopy continuation. You know all about this. We have a section in the paper. We talk a little bit about the running time here for d equals 3, n equals 8, depending on what the sigma is. The solving takes either fast or takes a little longer. Then, of course, there's certification. So, for example, here on this Grassmannian, it takes about 10 minutes to solve them. And there are 38,000 solutions. On a random try, 480 of them were real, and then the certification is quite fast. Okay. Now, Fabian's audience, they're scientists, so they like figures. Okay, so we put some figures in, right? So these figures show, how the bounds. So here's the number of spin orbitals. And then previous bound, our new bound, right? So previous bound, a logarithmic scale in blue. Our new bound is down there, and so on. And then we have an analysis of energy spectra from exact diagonalization. So we actually worked this out in the lithium hydride case. So exact diagonalization says we actually compute the 70 eigenvalues and eigenvectors of the matrix. So this gives the actual spectrum of 70 eigenvalues on the real line. And for CCS, or the Singleton-Grassmannian case, there's a pretty good match. So especially the lowest eigenvalue is approximated very well. For the CCD, it's a bit all over the place, so the match is not as good, And there you see in black complex conjugate pairs of the solutions. Anyway, so there's a discussion, right? So I'm not saying, let me make this very clear, I'm not saying coupled cluster theory is good or is bad. That's up for the chemists to decide. What we can do as algebraists, we can give them tools to make that decision. Yeah? We can give them tools that say, here is exactly how many solutions you have. You can look at these energy spectra. Sometimes it's good, sometimes it's bad. I think also this has to do with what the Hamiltonian is and so on. But there's an entire semester at IPAM to study these things. Yeah, so we had an in-depth discussion of lithium hydride. Maybe I'll skip this and I'll come. So this is the last slide. So we looked at this system of equations. I think that algebraic geometry, commutative algebra, combinatorics are essential ingredients for math and the sciences. We now know that polynomial equations with roughly 100,000 zeros can be solved routinely with certification. Right? So again, the numerical group led by Paul and John will explore this. Everybody loves Grassmannians and everybody loves Catalan numbers, right? So we didn't know in the beginning that they would come up, but topics that are familiar come up. Quantum chemistry, like other topics in the sciences, offers very interesting mathematical problems for commutative algebraists. Another comment is our equations, coupled cluster equations, make sense for every projective variety. Okay, let me explain this. Suppose you have a projective variety you like in a given coordinate system, right? And you have a basis of its algebraic matroid, right? So you pick a bunch of coordinates over which your varieties is algebraically independent. You have a Noether-normal system of coordinates, right? Well, you can do exactly the same thing, right? You look at the eigenvector equation, you truncate to those variables in the basis of the algebraic matroid, right? And you require that the eigenvector is on the variety, right? With that data, you have a notion of coupled cluster degree, right? So what we're saying here is, of course, came from this context, but you can study this independently for any projective variety. So you need a projective variety together with the basis of the algebraic matrix. And And yeah, well, random, let's say the couple cluster degree is for random symmetric or Hermitian, let's say symmetric or Hermitian matrix, but you have a degree. Now this blue thing is the title of this special semester that Frank and I got roped into. So this is called Numerical Algebraic Geometry and Correlated Electrons, Generalized Grassmannians, Response Functions, and Excited States. And I am an excited state. Thank you for your attention.